section, the chair is authorized to declare recess at any time. Before I want to deliver my opening remarks, I want to note, not surprisingly, that today the committee is meeting virtually. And a couple of other reminders to the members about the meeting. First, please keep your video feed on as long as you're present. If you have to come and go, just turn the video off and then come log back in. You're responsible for your own microphones. We are not going to micromanage you. Also, please keep them muted unless you're speaking. Finally, if you have documents that you wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing, and I'm sure all of your staff has that also. So good morning and welcome to today's hearing on a review of the Decadal Survey for Astronomy and Astrophysics in the 2020s. Welcome to our esteemed panel of witnesses. I'm very excited that you're here and really look forward to hearing from you. This is a joint hearing of the Subcommittee on Space and Aeronautics and the Subcommittee on Research and Technology. The NASA Aeronautics and Space Administration and the National Science Foundation jointly lead this nation's astronomy and astrophysics programs, one from space, one from the ground. So it only makes sense that we would jointly conduct this hearing. And I really want to thank Chairwoman Haley Stevens from Michigan for her collaboration on this joint hearing and on everything else. We live in a time of extraordinary discovery and progress in astronomy and astrophysics. That's the opening quote to the Decadal Survey, and a recognition that a fascinating future is on our horizon, one that could lead us to understanding the interconnections within the cosmic ecosystem across diverse structures, ranging from the tenuous gases at the boundaries of galaxies to the interiors of stars to our planetary systems. Our nation's investments in astronomy and astrophysics research and development have led to profound breakthroughs. Examples of discoveries over the past decade, which many of us on the Science Committee have enjoyed in almost first person. The first detection of gravitational radiation from astronomical sources, the discovery of thousands of planets beyond our solar systems or exoplanets, and precision measurements of the Milky Way's supermassive black hole, including a photo. The universe and the astronomical phenomena comprising it are vast, and the quantities of study are virtually infinite. This is why the National Academies once-a-decade surveys are so important. They focus the community's recommendations for scientific inquiry and prioritize the means of pursuing them, as well as the necessary investments required. So I'm delighted that both co-chairs of the National Academies Astronomy and Astrophysics Decadal Survey are here with us to discuss the report's important findings and recommendations. Their work in developing a scientific consensus is essential to our ability to support the nation's astronomy and astrophysics programs and our role as authorizers and even appropriators. It's the Decadal Survey that guides us as we seek to ensure the health and vibrancy of the discipline, the balance of programs that constitute agency activities, and the vision of those who study, investigate, theorize on some of the most profound questions of our time. And I'm really pleased that in this regard, the Decadal Survey examines the status of the profession too, expanding access to and diversity in inclusion in this community is a key to achieving the ambitious goals that this Decadal Survey lays out. As you know, IQ is spread across our entire human race, but we don't always get lured out for places that are underrepresented. The subcommittee I chair involves the space-based aspect of the Decadal Survey and NASA's role in it. NASA's on the cusp of realizing a major decadal priority with the upcoming launch later this month of the James Webb Space Telescope, 2 decades in the making. The Nancy Grace Roman Telescope, the old W1st, also a decadal priority, is making significant progress as well. I'm interested to hear what the Decadal Committee has learned from NASA's history of large-scale observatories and its recommended new approach to flagship missions with the Great Observatories Missions and Technology Maturation Program. Ultimately, we're going to need an acronym for that. While both space and ground-based activities are essential to realizing the Decadal Survey, transformational science and goals of understanding dark energy, dark matter, and potentially habitable worlds don't recognize a space or ground-based division. So I'm looking forward to hear from our witness on what the report recommends to reduce those divisions and to facilitate synergies across agency activities. Finally, I want to thank the community of astronomers and astrophysicists who contributed to the Decadal Survey, the amazing number of white papers, and all the steering committees and panels whose hard work, including through the pandemic, brings us this landmark report. Your efforts not only guide the future of the discipline, to inspire the next generation, many of whom will become our STEM leaders through the gateway of exploring our universe and the science of astronomy and astrophysics. I'd now like to ask for unanimous consent to enter into the record a letter from the American Astronomical Society. And seeing no objections, so ordered. So let me now recognize my good friend who represents the Johnson Space Center from Texas, the Honorable Mr. Babin, for his opening statement. Brian?
Thank you very much, Mr. Chairman. I appreciate you and ranking member and all subcommittee counterparts that are here today. And I also want to thank our distinguished witnesses. The National Academy of Sciences Decadal Surveys are an important part of our nation's space science program. They assess the current state of a specific space science fields, and they offer recommendations for the executive branch to implement and to manage, and for Congress to fund and oversee. The recently released report, Pathways to Discovery in Astronomy and Astrophysics for the 2020s, also known as Astro 2020, represents a multi-year engagement with the best and the brightest in our nation's astronomy and astrophysics communities. This same process informed the development of numerous ground and space-based observatories in the past, including the Very Large Array, the Chandra X-ray Observatory, the Very Long Baseline Array, the Hubble Space Telescope, the Spitzer Space Telescope, the Compton Gamma Ray Observatory, the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and the Vera Rubin Observatory, to name just a few. These observatories help us to understand the universe and reveal the fundamental science that makes up science and time. They are marvels of discovery and engineering that demonstrate American ingenuity and industry. In keeping with this tradition, the Astro 2020 Decadal proposes an ambitious program for the future. Aspirational and even audacious goals are important because great nations do great things. But astronomy and astrophysics are also areas that are well suited for cooperation, not just competition, as they benefit all of humanity and not just America. The Academy panel addresses the important balance of cooperation and leadership, and also lays out a compelling case for a portfolio of ambitious flagship missions and a robust baseline of smaller missions, technology, maturation, and research work that underpins the entire community. They also made a concerted effort to take cost estimating into consideration, including off-ramps and recommended prioritizations if further cost overruns or funding shortfalls do occur. This is important because, as we've seen over the last two decadal surveys for astronomy and astrophysics, cost overruns and delays impact on the rest of the whole enterprise. The health of our astronomy and astrophysics enterprise is important to the nation's overall industrial and scientific base. It takes time and decades of investments to create a skilled and knowledgeable workforce, robust supply chains, infrastructure, and institutions to support these cutting-edge technologies that push the state of the art. These same people, facilities, contractors, and institutions also support our national security and contribute to our economic and our technological future. But the health of this enterprise is undermined by cost overruns and schedule slips that not only delay the start of new flagship missions, but also potentially erode research and analysis funding and postpone the development of smaller, lower-cost missions that serve as a pipeline for early career scientists. Neither of the flagships recommended by the previous two decadal surveys have even flown yet. With any luck, Webb will launch later this month, but Roman recently exceeded its cost and schedule baseline and is not scheduled to launch until 2027. Unfortunately, this isn't a new problem, as the Government Accountability Office has listed NASA Acquisition Management on its high-risk series since its inception in 1990. NASA, NSF, and DoD all have research and development and acquisition policies designed to address this challenge. GAO and agency inspectors general have produced lessons learned, recommendations, and best practices. As we look toward the next decades, we should recognize that program management and execution are just as important to the space science sector as our people, our infrastructure, and our institutions. I'm excited to learn about what the community has in store for us in the coming decades. The launch of every new telescope and construction of every new observatory holds the promise of rewriting our textbooks and inspiring the next generation of scientists. I want to thank the witnesses for their important work, and I look forward to their testimony, and I yield back, Mr. Chairman.
Thank you, Chairman Babin, very much.
Yes, sir.
Let me now introduce Chairwoman Haley Stevens from Michigan.
Well, thank you, Chairman Beyer from the Commonwealth of Virginia. I'm from the state of Michigan, but it's great to be with the chair of the Aerospace Subcommittee on this particular topic. It's a real unique honor to be chairing this hearing with you. And of course, we are grateful to our distinguished panel for joining us today. And we thank everyone for this incredible body of work. The review of our goals for the coming decade are just going to have an enormous potential for the fields of astronomy and astrophysics. Some might remember last term in May of 2019, the full committee held a very exciting hearing to celebrate the first ever image of a black hole made by the NSF-funded Event Horizon Telescope. This was one of our better hearings, and I had the privilege of being there and meeting with the members of the scientific team that captured the image prior to the hearing. And we were all there with the enthusiasm of this scientist, and it was just truly infectious. So breakthroughs like the Event Horizon image just play an immeasurable role in inspiring students to pursue STEM studies, to bring people together, to help us reimagine our own society and our own work. And we can't help but be enthralled by the stunning images in astronomy and the implications for how we continue to understand our place in the universe. And I came away from that hearing inspired and re-energized and continue to bring that to this committee's role in advancing U.S. science and engineering. In that same discussion, we touched on a range of issues facing the astronomy community. We heard about the importance of investing in research infrastructure, from large-scale telescopes to smaller-scale instrumentation, and the people and the partnerships that play a role in that work. A breakthrough discovery like that would have not been possible without international collaboration and the talent of early career researchers. We also discussed the challenges related to the management of big data and the importance of investing in theory and simulations. And on the Research and Technology Subcommittee, we have a particular interest in the recommendations for the National Science Foundation from this study and the ground-based facilities that are needed for astronomers to address priority science questions. We have tremendous scientific opportunities before us, and I believe that this study has charted an exciting and yet achievable path for achieving big goals. I also appreciate the strong focus on programmatic balance woven throughout the report. It makes little sense to invest billions of dollars in research facilities if we don't also invest in students and researchers who can turn those capabilities into new knowledge. Another important focus for today's discussion will be understanding the needs of the astronomy community. I was pleased to see a particular focus in this report on the future of the astronomy workforce, with an emphasis on addressing barriers to diversity and inclusion. Under the leadership of Chairwoman Johnson and Ranking Member Lucas, STEM diversity has been a cornerstone issue for this committee. We remain eager to learn more about the vision of the community and the goals that you have set for yourself, and to better understand how Congress can help you realize these goals. You have done your part, and now it is our turn to address the needs, to bring the agencies together, and continue to look forward to a very vibrant future, one that addresses the material needs, the scientific needs, and the ways in which we can harness collaborative research efforts. So thank you so much, and I'll yield back.
Thank you, Chairperson Stevens, very much. And now finally we hear from Ranking Member Waltz from the Energy Subcommittee. Mr. Waltz, you're...
Hey, thank you, Chairman Beyer, and Chairwoman Stevens, Ranking Member Babin. I too am pleased to be here for this joint subcommittee hearing to review the National Academies' recommendations, priorities on their survey on astronomy and astrophysics, Astro 2020. We all know, but I always think it's worth restating, that the National Science Foundation is the federal steward for ground-based astronomy in the U.S. and has supported some tremendous achievements in astronomy and astrophysics. These include the detection of gravitational waves at the LIGO Observatory, which actually proved part of Einstein's theory of relativity. It launched a new era of multi-messenger astrophysics and earned the 2017 Nobel Peace Prize in Physics. And in 2019, the Even Horizon Telescope project captured the first ever image of a black hole, providing further confirmation of Einstein's theory of general relativity. And as I expect we'll hear and discuss today, many of NSF's most interesting astronomy projects are yet to come. The Vera C. Rubin Observatory in Chile has the potential to advance every field of astronomical study, from the inner solar system to the large-scale structure of the universe. And the DKIST is also the telescope is also expected to come online soon in Hawaii. It will produce the most detailed images of the sun ever taken by a ground-based device. As we look to the future, I would be remiss if I did not also take a moment to speak on the legacy of the Arecibo Observatory in Puerto Rico, which experienced an unexpected and catastrophic collapse exactly 1 year ago today. Before its collapse, countless discoveries were made at Arecibo over its nearly 60-year history, including winning the 1993 Nobel Peace Prize in Physics. And I, along with Congresswoman Gonzalez Colon and several other members, had the opportunity to visit Arecibo this past summer. We saw the extensive damage and the ongoing cleanup. But what really stood out to me was the importance of the facility to the community in Puerto Rico and increasing diversity in STEM, as Chairwoman Stevens just referenced. And while we were there, we joined several local high school and STAR Academy students for lunch. These were just amazing kids. And as a supporter of increasing diversity in STEM, it was great to see so many young women, in particular, all native Spanish speakers, and each student shared their experience conducting hands-on research projects at the observatory and their plans for pursuing STEM degrees after high school. In short, they blew me away, made me feel a lot dumber, but were really some of the most impressive students I've talked to in a long time. And the trip made clear, I think, to all of us that Arecibo is an important complement and critical to this committee's bipartisan tradition of promoting diversity in STEM, including the MSI STEM Achievement Act that the chairwoman and I ushered through the House this Congress. So I strongly believe that to meet our true scientific and technological potential, we need an inclusive and diverse workforce. It draws on the full talent pool available in this country. And sitting down with these students, I saw this happening in real time and achieving these goals at Arecibo. And the observatory's engagement in the community through STEM education and outreach should be applauded, exemplified, and supported by this committee. I was pleased to see that the Astro 2020 survey recognizes that Arecibo has a future role in U.S. astronomy, although I have concerns that the United States, like we have in so many other areas, has ceded leadership in radio astronomy to the Chinese Communist Party. For those who don't know, they now have the largest radio telescope in the world, known as FAST. The U.S. should not obviously rely on the capabilities of the CCP to excel in radio astronomy. So I look forward to working with the NSF as they continue to examine the future of Arecibo, and I hope we can accelerate that examination and make some decisions soon. Like Arecibo, the NSF's astronomy program focuses on questions going forward. The NSF must evaluate, I think, how it supports existing and new facilities, including identifying facilities that may be nearing the end of its life cycle, and then examining how we balance those commitments in operation and maintenance with funding individual research grants that will support the next generation of Nobel Prize winning astronomers. So I want to thank the survey's co-chairs for participating along with GAO. I look forward to hearing how we can continue our commitment to the fundamental nature of research and understanding the universe. I thank you. I yield back the balance of my time.
Thank you, Ranking Member Waltz, very much. I'm sure you were just as smart as they were when you were that age.
No, I wasn't. Not even close. But they were quite impressive. Thanks.
That's wonderful. If there are other members who wish to submit additional opening statements, your statements will be added to the record at this point. Just please send them to the clerk. So this time I'd like to introduce our witnesses. Dr. Robert Kennicutt is a professor at the Stewart Observatory at the University of Arizona and in the Department of Physics and Astronomy at Texas A&M University. His research interests are primarily observational extragalactic astronomy and cosmology. He served on various committees at the National Academies, including the Committee on Astronomy and Astrophysics and the Task Group on Space Astronomy and Astrophysics. He also currently serves as the co-chair of the National Academies Committee for a Decadal Survey on Astronomy and Astrophysics 2020. Hence your invitation today. We're very pleased to have the co-chair with us. Dr. Kennicutt received his PhD in astronomy from the University of Washington. Dr. Fiona Harrison is a professor of physics and chair of the Division of Physics, Mathematics, and Astronomy at the California Institute of Technology. Dr. Harrison's primary research interests are in experimental and observational high-energy astrophysics. She served as chair of the National Academy's Space Studies Board, was a member of the James Webb Space Telescope Independent Review Board, and chaired the National Academy's Committee on an assessment of the astrophysics-focused telescope assets mission concepts. She also serves as a co-chair. She's the other co-chair of the National Academy's Committee for a Decadal Survey on the Astronomy and Astrophysics 2020. So we have both of the big dogs on this really, really important survey. Dr. Harrison has her PhD in physics from the University of California at Berkeley. And finally, we have Mr. William Russell. He's the director in GAO's Contracting and National Security Acquisitions team. So he's the one who holds everyone accountable. He oversees a portfolio of issues related to NASA, DoD weapon systems, cybersecurity, protection of critical technologies, DoD industrial base and supply chain integrity, defense contracting, and the use of the Defense Production Act to support the federal response to COVID-19. Mr. Russell has a master's degree in foreign affairs from the University of Virginia, simply known as the university here in the Commonwealth, and a bachelor's degree in political science from Virginia Commonwealth University. As the witnesses should know, you each have 5 minutes for your spoken testimony. Your written testimony can be and probably is much longer, and that will be included in the record for the hearing. When you've completed your spoken testimony, we will begin questions. And each member will have 5 minutes to question the panel. So let's begin with Dr. Robert Kennicutt. Dr. Kennicutt, the floor is yours.
Mr. Chairman, Madam Chairwoman, Ranking Member Babin, Ranking Member Waltz, and members of the subcommittee, thank you for the opportunity to appear today to speak to you. The Decadal Survey for Astronomy and Astrophysics in the 2020s, which charged to develop and recommend a broad scientific vision and plan for space and ground-based astronomy and astrophysics over the coming decade. The report is a culmination of a 3-year community-based exercise informed by the work of 13 expert panels and 860 community-authored white papers. It lays out a scientific agenda addressing some of the most fundamental and profound questions in our exploration of the cosmos, along with a recommended program of investments aimed at answering those questions. Along the way, difficult choices had to be made, as the wish list of ideas and projects proposed to us exceeded by severalfold the resources available. We thus have tempered ambition with realism by setting firm priorities and guidance for the agencies, while also providing flexibility for them to adapt to changing landscapes over the decade. Mr. Chairman, we do live in an extraordinary period of discovery in astronomy and astrophysics. 6 of the Nobel Prizes for physics awarded over the past decade involved astronomical data, and subjects ranging from planets around other stars to dark energy and the birth of our universe. This rich Nobel harvest will be difficult to sustain, but there's every reason to believe that the pace of discovery will continue unabated over the coming decade. Our survey identifies 3 major areas which are especially ripe for breakthroughs, and I'll describe the first 2. The first goal is pathways to habitable worlds, the quest to identify and study other planets in the universe, including potentially habitable and life-bearing planets like our own. To date, more than 4,800 planets have been identified, including potential Earth analogs. One of the most profound questions that we as humans can ask is, are we alone? Could life exist on planets orbiting other stars besides our sun? Today, thanks to investments in technology, including the coronagraph on the Nancy Grace Roman Space Telescope, we are poised to develop a space mission that can image some of these other worlds directly and measure the atmospheres of those pale blue dots, whatever color they turn out to be, searching for molecules produced by life. Accomplishing that goal is challenging. Detecting a distant Earth-like planet against the glare of a star like the sun requires high contrast imaging at the level of 10 billion to 1. But the goal is within our reach, and we recommend the development and maturation of such a mission as our top large space priority. In the meantime, a new generation of ground-based extremely large telescopes, or ELTs, with apertures of 20 to 40 meters, should be able to image habitable zone planets around fainter stars than the sun, where the contrast requirements are lower. And we recommend NSF partnership in the 2 US-led ELT projects as our top large ground-based priority. The next of our science goals, unveiling the drivers of galaxy growth, addresses the fundamental question of our origins, the formation of the stars, planets, galaxies in the universe and the universe itself. We now realize that these formation processes are tightly interconnected in a kind of grand cosmic ecosystem. The seeds of galaxies were planted during the first moments of the Big Bang, and modern numerical simulations can retrace the gravitational growth of those seeds into galaxies from 300,000 years after the Big Bang till today. The galaxies, in turn, are ecosystems of their own, with matter condensing to form stars and central supermassive black holes, balanced by feedback of energy and matter from those stars and the black holes, which refuel the formation cycle and reshape the galaxies. Later this month, the James Webb Space Telescope will embark on its quest to directly retrace this history of cosmic star and galaxy formation from the first objects formed to the present day. Following Webb, the same large space and ground-based telescopes already described for imaging exoplanets will provide transformative observations of the manner and energy flows powering this growth in galaxies. Other insights will come from deep radio observations of galaxies with the next generation very large array, far infrared observations of star and planet forming clouds, and X-ray observations of the galaxies and their massive black holes. That concludes my remarks. Thank you again for the opportunity to testify.
Dr. Kennicutt, thank you very much. We'll now move on to Dr. Harrison. Professor, your floor is yours.
Thank you, Mr. Chairman, Madam Chairwoman, Ranking Member Babin, Ranking Member Waltz, and members of the subcommittees. I'm really grateful for the opportunity to tell you about our survey. And I'm going to pick up where Rob left off, and that's to tell you about our third priority science area, new windows on the dynamic universe. So this really captures the broad range of science that's enabled by observing the sky in new ways that have only become possible in the last 10 years. One of the most dramatic scientific events that has been alluded to already is the first detection of gravitational waves by LIGO in 2015. And this was from 2 black holes that 1.3 billion light years ago merged into one. And this event, unbelievably, was detected by sensing minute, tiny ripples in the fabric of space and time itself that was created in this merger. So gravitational waves in general are produced by very dense objects, black holes and neutron stars, when they orbit around each other and eventually merge. And if one of these objects happens to be a neutron star, light can accompany the gravitational wave signal. And so in one watershed event in 2017, light was seen from such an event all the way from radio waves up to the gamma rays. And studying these events and the complementary messengers of gravitational waves and light will reshape our understanding of topics as diverse as the origin of carbon in our bones, the heavy elements like in your wedding ring, to the history of the expansion of the universe since the Big Bang, and the physics of black hole event horizons. So searching for these light signals and also searching for light signals that accompany detections of elusive, almost massless high-energy neutrinos, which are detected by the Antarctic Ice Cube Observatory, is another opportunity to combine fundamentally new and different kinds of information to study the most energetic particle accelerators in the universe. So actually, immediately capitalizing on the gravitational wave and neutrino opportunities doesn't require a large mission or telescope, but rather programs that consist of suites of coordinated small and medium scale observatories that can quickly train themselves on the region where these events happen and quickly study the light that come from these transient phenomena. And the same suite of time domain facilities can also be powerful for following up explosive events that will be discovered in droves with the Vera C. Rubin telescope when it comes online in the next few years. So another opportunity in new windows is to make very sensitive observations of the relic radiation from the Big Bang itself. This is the cosmic microwave background. And what we're looking for is the imprint of gravitational waves that are produced in the very, very earliest moments of rapid expansion in the universe, a period known as inflation. This will certainly be a Nobel Prize if it's discovered. And this can be achieved with the CMBS-4 Observatory, which is a moderate scale joint Department of Energy NSF effort. So while these large projects provide major new observational capabilities, it's already well recognized by this committee that achieving a broad scientific program, being able to respond nimbly to new scientific discoveries, this requires a whole range of mission scales. Small and medium-sized projects can be developed and deployed on few-year timescales, harnessing the ingenuity of the entire community. They can deploy new technologies rapidly and serve as test beds for future large strategic endeavors. So our report envisions robust ways for achieving and strengthening this programmatic balance by recommending that NSF expand its mid-scale programs and that NASA emphasize continued strong support for its Competed Explorer program, and also add a competed line of probe scale missions that serve as intermediates between the smaller explorers and the large strategic missions. And so finally, the survey identifies important ways to foster the development of human capital, the research infrastructure, and future technology. Developing and diversifying the scientific workforce is a pressing need that's already been identified, and bridge programs help students from all backgrounds get the skills and knowledge they need to pursue advanced degrees. Also, supporting individual investigators is essential, and here we emphasize increasing grants at the NSF. And also, finally, early stage technology development is essential for our future. And so I thank you again for the opportunity to share the highlights from the Decadal report.
Thank you, Dr. Harrison, very much. And finally, we'll hear from Mr. Russell from the GAO. Mr. Russell.
Chairman Beyer, Chairwoman Stevens, ranking members Babin and Waltz, and members of the subcommittees. I'm pleased to be here today to discuss the 2020 Decadal Survey on Astronomy and Astrophysics. Decadal surveys are a key input NASA uses to determine its science missions. Three major projects in NASA's portfolio, the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and Sphere-X, are derived from past surveys. These telescopes are pivotal to NASA achieving its science mission, such as seeking to understand the universe and our place in it. As Congress, NASA, and the science community consider future projects, It'll be important that new programs are managed in a manner that minimizes cost overruns and schedule delays. NASA's telescopes and other science projects will always have inherent technical, design, and integration risks because they are so complex, specialized, and often push the state-of-the-art in space technology. But too often, our reports find that management and oversight problems, which can include poor planning and optimistic cost estimating, are the real drivers behind cost growth and schedule delays. For example, James Webb's launch date has been delayed by over 7 years, and costs have nearly doubled to almost $10 billion. Acquisition management remains a long-standing challenge at NASA, and in our March 2021 high-risk update, we found that NASA still needs to do more to reduce acquisition risk and demonstrate progress, especially with cost and schedule performance on large and complex programs entering the portfolio. NASA recognizes these challenges and is taking steps to identify and address areas contributing to this acquisition risk. For example, in March 2021, we found that NASA had taken steps to improve transparency and monitoring of project costs and schedules. Today, I'd like to highlight 3 lessons from our reviews of NASA's major projects that can be applied to future efforts as NASA considers this decadal study. First, NASA could better manage cost and schedule performance for some of its large flagship projects. NASA's most costly and complex missions have had cascading effects on the rest of the portfolio. For example, James Webb's cost growth had an outsized effect on the rest of NASA's major acquisition portfolio and required NASA to identify more than $1.4 billion in additional resources from other efforts, such as the Science Mission Directorate account, to offset these costs. In essence, NASA had to trade future missions and research to address Webb's resource needs. Second, NASA can better minimize risk in its programmatic decisions. NASA leadership has at times made programmatic decisions that compound technical challenges. These decisions include establishing insufficient cost and schedule reserves, approving baselines that do not fully follow best practices, and proceeding with immature technologies. Last, NASA can continue to regularly and consistently update cost and schedule information. NASA took a positive step in 2019 by updating its Joint Cost and Schedule Confidence Level Policy to help ensure that estimates are realistic and projects are thoroughly planning for anticipated risks. NASA's most expensive projects will also update their estimates more frequently as risks change. It will be important for NASA to fully implement this policy moving forward so decision makers have realistic and up-to-date estimates as projects move through their development. In closing, the most recent Decadal Survey continues to encourage NASA to pursue transformative capabilities, including a new space telescope. As NASA considers the survey's recommendations, there's an opportunity to learn from the challenges of Webb and other projects and help better position future space telescopes for successful outcomes. We look forward to continuing to work with NASA and these subcommittees in addressing these important issues. Chairman Beyer, Chairwoman Stevens, ranking members Babin and Waltz, and members of the subcommittees, this completes my prepared remarks. I look forward to responding to your questions.
Mr. Russell, thank you very much. We'll now move on to questions from the members of Congress. I have the privilege of going first, to be followed by Ranking Member Babin and then Chairwoman Stevens. I only have 9 questions for you in my 5 minutes. So let me begin with Dr. Harrison. In the written testimony, they talked about how new messengers and new physics will exploit the new observational tools of gravitational waves and particles. Have we actually found a gravitational particle yet, a graviton? Or are we're just hoping that we'll find one?
Yeah, we have not. In fact, the particles we're alluding to, of course, are the high energy neutrinos, but it's a forefront area of physics to study quantum gravity and try to understand the nature of the graviton. So gravitational wave observations do place some limits on how fast they travel. We think very, very close to the speed of light. Whether it's exactly the speed of light, LIGO may tell us. But combined with light may tell us.
But given wave particle duality, you haven't given up looking for a graviton.
No.
Okay, good. You'll make sure. Dr. Kennicutt, I read this wonderful book by Emma Chapman called First Light, Switching on Stars at the Dawn of Time earlier this year. And she talked about how the science was able to put together these cosmic webs of dark matter, and that where the dark matter webs, where there were dense overlaps, was where you would think of galaxies beginning. How do you measure dark energy, and how will you see these webs? What kind of tools are available for that?
Yeah, what you said is exactly right. This is simulated numerically. Most of the dark matter dominates the total mass of particles several times more than ordinary matter. So early in the growth of the structures, it's the dark matter that forms the structures. But the ordinary matter, which if it condenses into galaxies, follows along for the ride. And so we can trace the structure directly through the distribution of galaxies in the sky. We're also beginning to be able to do it through a technique of gravitational lensing, which maps the dark matter directly. That part of the physics is very well understood. And the goal of the ecosystems is to the physics of the gas. What happens to the gas after that is the hard part. And the models make predictions, but the physics isn't fully understood. And so that's where the cutting edge is, and that's what we aim to study over the next decade.
Well, it'll be fascinating and fun, I'm certain. Mr. Russell, in the survey, it talks about commencing mission and technology maturation of a far IR and an X-ray large strategic mission, both scoped to have implementation costs in the $3 billion to $5 billion range. How are we going to do this great observation stuff with $3 to $5 million when James Webb costs us $10 million?
That's the key point, Chairman Beyer. I think, as you saw with James Webb, the initial estimates were $1 billion to $3.5 billion, and here we are, hopefully launching later this month, at about $10 billion in the cost. So I think the technology maturation efforts proposed in the decadal make a lot of sense. Our own lessons learned and best practices suggest that if you can get technologies to TRL6, which is where you can demonstrate a prototype in a relevant environment, that's gives you all the markers for successful outcomes going forward into implementation. So to the extent that those maturation efforts can lead to that kind of technology development, that could be a good thing. But we'll have to keep an eye on the cost. $3 to $5 billion. Having good realistic cost estimates behind some of those as they proceed through their development will be important.
Yeah.
Chairman Beyer, may I add something brief?
Yes, please, Dr. Harrison.
Yeah, I think part of what the survey really said is you need a new phasing between decadal surveys and telling NASA they should adopt a mission. And so this sets a cost target of 3 to 5, and there's a review. And if they don't meet that cost target, then they don't get recommended by, the follow-up process. And so this is a new mechanism that we're trying to ensure that missions are initially scoped correctly for what a decadal survey feels they should be. In the case of the large UVOIR, we recognize that's a very large, that's a web scale mission. But in these other cases, that's the point of the maturation program.
Great. It's a very helpful explanation. Thank you very much. My time is up, so let me recognize the good congressperson from Texas, Mr. Pat.
Thank you, Chairman Don. I appreciate you. Mr. Russell, I'd like to address the first question to you. The 2020 Decadal Survey recommends a new $11 billion space telescope. The 2000 Decadal Survey recommended the James Webb Space Telescope that has yet to launch. The 2010 Decadal Survey recommended the Rosen telescope, which is still in the early stages of development. Both telescopes have incurred significant cost and schedule increases. Are there any lessons to be learned to NASA that NASA should keep in mind for future space telescope efforts? And what best practices should NASA adhere to if it pursues this large, complex program?
Thank you for the question.
Briefly, if you could. Yes, sir.
Certainly. Just a couple of quick takeaways. One, NASA's already embedded into its policy doing more of those joint cost and schedule confidence levels. Those give you good point in time estimates you can use to calibrate changes that are going to be needed for risks that have occurred on a program. That's a good step. So if NASA could pay attention and focus its efforts on any future projects to do those in a timely way, that's good. Also to have realistic cost and schedule baselines as they're deciding on programs to go into implementation is another lesson learned. Sometimes we've seen overly optimistic cost estimates, which can lead to cost overruns later on. And then briefly, making sure you have good mature technologies when you baseline those programs, and if not, have some off ramps and backups in case those technologies don't mature as anticipated.
Thank you very much. And now, Dr. Harrison, I'd like to talk about a possible space telescope gap risk. The recommendations contained in Astro 2020 span not only the coming decade, but it will also likely influence the following decade as well. While we anxiously await the launch of JWST later this month, I'm reminded that it was recommended by the 2000 Decadal Survey, and the Roman telescope was recommended by the 2010 Decadal Survey as a quick way to achieve fantastic scientific goals given the delays to JWST. We are now seeing delays to even Roman. Understanding that these are complicated undertakings and is there a risk to recommending a multi-decade mission when we're decades behind on our current programs? And if it weren't for multiple Hubble servicing missions that fixed initial problems and extended the life of the mission longer than anticipated, we would be experiencing a gap in that flagship astronomy mission as well right now. How should the community mitigate the risk of an extended gap in flagship astronomy and astrophysics missions if Hubble becomes inoperable and the current or future missions experience further delays or even failures? And what impact would that gap have on the U.S. Astronomy and Astrophysics community? Briefly, if you'd give us your opinion.
Yeah, so very, very briefly, that's a wonderful question, and it's one the survey struggled with greatly. And the opportunity to find habitable worlds and find life outside of our solar system is so compelling. But it is a large mission, and we said, don't adopt it now. NASA, do not start it now. Take 5, 6, if it's needed 7 years to co-mature it, really get the cost under your belt, understand it, and then adopt it. That's to mitigate the risk of the large overruns, which is very damaging to the program. How are we going to fill that gap in between? And that's why we have these probe missions. They're capped at $1.5 billion to NASA. They can launch on decade timescales because they will be more focused. They will have mature technologies, and that will enable us to really keep the progress of capable space observations while we're developing the large mission.
Yes, ma'am. Thank you very much. And now to go to our Aggie professor there, Dr. Kennicutt. The survey recommended an unprecedented level of NSF investment that would provide $1.6 billion split between the consortia constructing the Giant Magellan Telescope and the 30-meter telescope, or TMT. Is China still a partner in TMT? And if so, is it still responsible for polishing the mirror segments? And then I have a follow-up question about what impact would a formal commitment from the U.S. government towards TMT construction, not just use, have on China's ability to develop advanced mirrors and optics for their national security purposes? And how could the TMT consortium ensure that U.S. funding does not advance Chinese military capabilities or subject U.S. technology to theft or exploitation by the CCP?
I realize I have to answer quickly. To my understanding, they formally remain a partner in the TMT project. Understand that Fiona and I are involved in GMT and TMT institutions. We had conflict. We have stayed away from those projects. I share your personally your views that this cannot benefit military applications in the future. But I think that's an issue that the NSF would have to resolve with the project. It's not something, it was outside of the scope of we thought we were charged to take up.
Okay, thank you very much. Mr. Chairman, I yield back.
Thank you very much. I mean, I recognized Chairwoman Stevens.
Thank you. Dr. Kennicutt, I'm very excited about the scientific opportunities by the large-scale ground-based facilities, and just want to make sure we're understanding the immense cost of operating them. So your top priority recommendation, the extremely large telescope program, would require about $32 million per year in operations funding from the National Science Foundation. The survey highlights the NSF's approach for funding facility operations and construction as maybe an area for concern. So could you walk us through that a little bit? Oh, we got you on mute.
Yeah.
There we go.
I'm unmuted now, right? Yeah, thank you for that question. I really appreciate the opportunity. The problem you identify is a really big one for the NSF, one they recognize. As we build more of these facilities, the cost of operating, maintaining all of them has slowly been creeping up. And there's a concern that the fraction of the NSF allocation for astronomy and astrophysics is being taken up to the point that those costs are eroding support for grants, programs, technology development, and so on. And so all of the projects we recommend have what we call decision rules, conditions that apply. And a recommendation we make that applies to every NGVLA, the ELTs and CMBS-4 is that as NSF, contemplates these new missions, they have to consider the full cost implications of building them and develop a plan. For the case of the ELTs, where will that $32 million a year come from? Their current total budget is in the order of $300 million. So it's not intended to be insurmountable, a showstopper, but it's a problem that's been eroding away and just has to be addressed.
We're talking about a 30% to the NSF increase for the astrophysics division, and obviously the need and the pressure for that, and then the top recommendation for ground-based frontier facilities is a federal investment in at least one, but ideally both of the extremely large telescope projects, namely 30-meter and the Magellan and the Giant Magellan. And so they're similar in size and have similar capabilities, but, and maybe Dr. Harrison can get in here too, but along with you, Dr. K, just any explanation about the benefits of having both telescopes operating in concert and what would be lost if only one was supported.
Fiona, would you like to take that?
Why don't you go ahead and start, and I'll fill in.
Sure. Yeah. So there are a number of benefits to both. For one thing, there's only probably 20 to 25% of the time available on either one because they've already signed up a large number of other partners. And so if you can get involved in both, you essentially double the amount of observing time, number of nights a year that the U.S. community will be able to observe on these telescopes. Also, having access to the northern southern hemispheres means no event in the sky will go unobserved. And also there are benefits of complementary instrumentation on the synergies between the two and coordination. Those are the main reasons for favoring two. But if only one project proves to be viable, then we've recommended NSF pursue as big a share of time on the one that is there as possible.
Yeah, I don't have anything to add.
And so we're going to have the capabilities of the combination of these telescopes, and we've got another one under construction in the European Southern Observatory too. So is that the same sort of thing, Dr. K, where we're going to get the ability to capture these images, in any other relevance in terms of that comparison with the European Southern
This is an
Observatory?
area where Europe has has gone a bit ahead. Theirs is a somewhat larger telescope, 39 meters. It's suffered its own delays due to all sorts of reasons. We'll probably commission ahead, but the amount of science to be done on these telescopes is immense. Europe had the same debate when the two Keck telescopes were built 25 years ago. Should they build their 4 8-meter telescopes? Now there are 18, I believe, Keck class telescopes in the world, and it's difficult to get time on essentially all of them.
Yeah.
So,
yeah. Well, that's great. Well, thank you both so much, and to everyone. And Mr. Chair, I yield back.
Thank you, Chairwoman Stevens. Ranking Member Waltz is up next, if he is present. A second. If not, let's move then to Congressman Meyer. Peter, the floor is yours.
Thank you, Mr. Chairman. Thank you for all of our witnesses who are here today and for the opportunity to dive deeper into an area that I will confess I had only rudimentary knowledge of before joining this committee. But I think, as Mr. Waltz was saying about Arecibo and some of the challenges we have in terms of being able to compete in this realm with China, to be able to continue to gain upon the advances that have been made in decades past, to make sure that that growth is exponential going forward. I think this is a very relevant, timely, and important topic for us to be reviewing. A few questions for either Dr. Harrison or Dr. Kennicutt. The Decadal Survey highlights a concerning issue with the way NSF funds its programs as it budgets for the constructions and the operations through separate funding streams. We've seen this funding method financially limit NSF's ability to fund research grants and other science programs when those construction costs run high. And obviously, even before the current inflationary environment we're in right now, it's always been the challenge of that projection on where costs will be relative to expectations. How do you believe NSF can create a more balanced funding mechanism that can give both predictability and make sure that future costs are better anticipated?
Rob, do you want to take that, or do you want me to?
go ahead, Fiona. Why don't you take this turn?
Yeah, so, there's always been a structural issue at the National Science Foundation in that construction and operations are very separate lines. And so it's hard for a survey to really understand all the implications of changing that mechanism. For example, you could build operations into the congressional line that funds construction, but that has its pluses and minuses. There may be other mechanisms. So we feel that the agencies working with the National Science Board and Congress need to evaluate those mechanisms and come up with a solution, but we don't dictate that solution. And so I think you're absolutely right. It's anticipating more accurately the construction costs, which I believe that NSF is making progress with, and also anticipating the operations costs and building them in a sensible way, either to the astronomy budget or to the MREFC, the line that funds the construction. And I think either of those is viable.
Congressman, could I add a bit to that?
Please.
Yes, I think the situation is a bit different in NSF. I think the history of construction costs shows that actually their projects tend to come on board for cost much better than many of the NASA flagships. The real problems are somewhat different. One is the very long lifetimes of their facilities. And also, facilities tend not to be shut down at as large a rate as a space mission, of course, where they degrade more rapidly. One recommendation we make is to follow the lead of NASA. NASA reviews its operating missions every 3 years, and what they call a senior review. NSF did this about 10 years ago with what they call the portfolio review. We've encouraged them to hold reviews of their whole suite of operating facilities more often. so they can be looked and compared in a kind of a competitive environment. And that we hope might help alleviate the problem over the long run.
And the point on the longevity of these assets, I think, is very well taken, especially the need to be focusing then on enduring and preventative maintenance, so that that lifetime could be extended, especially as some of these platforms are able to be further modified, upgraded to reflect advances that we have. My time is running a little bit short, but I guess any kind of last words on this question when it comes to then incorporating preventative maintenance, presumably into an operation schedule, but would it be most helpful to have those periodic reviews to get that across that asset class, or just any thoughts you might have?
I can chime in there because I have a space mission and we undergo these regular 3-year senior reviews. And that does look not only at what improvements and enhancements are needed, what maintenance is needed, and how could budgets be streamlined by perhaps for older observatories, is it appropriate to take a little more risk? And so I think that's the balance that those portfolio reviews or regular reviews bring.
Thank you. With that, I yield back.
Thank you, Congressman Meyer. I now recognize Dr. Foster, but before doing that, just note that we probably have time for a second round. So you don't need to cram all 9 questions into the 5 minutes if you need to. Congressman Foster.
Yeah, thank you, Mr. Chairman. I appreciate that and I intend to capitalize on that. And first, I want to second Dr. Harrison's endorsement of having multi-messenger and targets of opportunity be a big part of this. I got my PhD thesis building a proton decay detector, the first of the giant underground detectors, and doing Planck scale physics, and then ended up in our sensitivity to supernova was sort of a standing joke among all the grad students. And then lo and behold, in 1987, actually we finally got the radiation from a supernova that went off 160,000 years ago. And so we saw in our underground detector the neutrinos, and at the same time the optical astronomers saw the optical signal and learned a lot about supernova. And so it's good that you maintain the flexibility and the agility that you get from these multiple maybe smaller things. So I definitely endorse that. Now, when you're doing things like decadal surveys, it's an easier thing to design if the United States is the only show in town, and it's not anymore. And so this makes you sensitive not only to cost and schedule or delays, basically, in the US program, but in having correct predictions of when scientific competitors will actually do these things, because you can mess up either way. If you accept at face value the schedules for competing experiments, you may be under ambitious because you'll just say, well, we can't possibly compete with that. And I can certainly point to things in my career where that mistake has been made. And so how do you evaluate not only your realistic cost and schedule estimates, but those of the EU, Japan, and other competitors? Where do you get that input from?
Rob, do you want to take a first?
Yeah, I'll start. It's a great question. A question we're often asked is, why didn't we give really specific timelines and roadmaps, direct to NASA, for example, do this mission in 2023 and the next one in 2027 and so on. And it's for the very reasons you described. Landscapes change, funding landscapes, international landscapes change, and so on. So what we try to do is lay out broad roadmaps and guidelines and leave the detail to them. Fortunately, this time, at least for space, Europe just completed its own exercise. It's called Voyage 2050, and they've laid out a set of priorities. They announced their outcome just as we were finishing ours. So, but in fact, there are some projects in common. There will certainly be collaborations. A little known, well over half of the NASA portfolio of missions involve international partners. And we hope that will continue. Part of the issue of the gap that was raised earlier before the next big flagship is that the U.S. is a partner in the LISA Gravitational Wave Observatory, the Athena X-ray Observatory, all European-led, but with partnerships from NASA. I'll stop there and just see if Fiona wants to add anything.
Yeah, well, I'll just go direct to your point. Would you make a mistake by just giving up because Europe's doing it? And I think that the ELTs is a perfect case in point because yes, Europe is pursuing a large telescope, in fact, larger than the ones we've envisioned. Should you just say, okay, even though this is an area where the US is led, we're just going to let Europe do the, big thing and we'll go off and find some other corner? No, absolutely not. This is the forefront. This is the vision. We know that by being inventive and innovative with instrumentation, technologies, we build these telescopes, we can keep refreshing them in creative ways that keep us absolutely competitive with the European efforts. And it's not just a competition. I imagine the way this will evolve is Europe will choose particular instruments on their telescope and we'll choose different ones on ours. And, this pushes the forefront of science cooperatively worldwide.
Okay. Yeah. So it's complicated, and you can. So thank you for taking a swing at that. And it gets even more complicated when you have less transparent competitors like China enter into it, where you simply don't have the level of communication you have with the Europeans. Anyway, so I thank the chairman for the second round of questions that I anticipate, and at this point I'll yield back.
Thank you, Dr. Foster, very much. Next, if our ranking member Waltz is with us, so Congressman Waltz, the floor is yours.
Hey, thank you. And Dr. Kennicutt, the first question I want to throw your direction. In the middle of the survey, and as I mentioned in my opening statement a year ago today, the Arecibo Observatory experienced an unexpected and catastrophic loss and collapse. Excuse me. My understanding is the survey steering committee assessed the impact of Arecibo's loss on the key science questions and programs. Are there future opportunities for continued utilization of the Arecibo site for radio astronomy? And can you discuss the potential opportunities for the future of Arecibo?
Absolutely. The loss occurred at a very awkward time for the survey, to the extent there was no way you could actually do a full review, of course, of all the possibilities. But we did look very closely with help for our radio panel at the scientific impacts. We think there is a bright future for Arecibo. The example that we think is the most attractive is as a major part of the NGVLA, the Next Generation VLA site. As you probably know, the VLA currently is based in New Mexico. New Mexico isn't big enough to hold the NGVLA. The NGVLA will cover the entire country, at least the major part of the northern hemisphere of our hemisphere, and already there were preliminary plans to site some of the dishes and so on there. That would provide it front and center at what will be the cutting edge of radio astronomy in the coming years. The other element we think is very important is the outreach efforts, all of the community engagement. This is a community that values what Arecibo brought there, and we want to see that preserved. I don't know if that answers all of your questions, sir.
No, it does. I wanted to get Dr. Harrison's perspective on the loss as well. I mean, as we know, is the most powerful, or it included the loss of the most powerful planetary radar in the world. And it affects our capabilities. Again, correct me if I have a misunderstanding, but it affects our capabilities to accurately map the surface of planets and predict orbits for potentially hazardous asteroids. And so I think you mentioned, you just got at the issue, but Dr. Harrison wanted to get your take as well, on which existing instruments have similar sensitivity capability and availability to fulfill the role that AO had, and how does the committee suggest we continue our planetary defense actions against near-Earth objects?
Yeah, that's a great question. And so first, let me say that our remit was astronomy and astrophysics. And so we didn't have as part of our charge to look at the other aspects like planetary defense. And, Arecibo, of course, had a broad range of things that it was doing. Our task was to look at the impact on astronomy and astrophysics. And so I'm afraid I'll have to not answer that part of your question, but just say, as far as astronomy and astrophysics go, Arecibo was key in timing pulsars, which is another way to detect gravitational waves. And so that will be a gap in our capability, but increased investments in the Green Bank telescope to do that, and international cooperation will tide us over until the point where we have the next generation VLA, which is absolutely essential for keeping our leadership in radio astronomy. And so, with the focused lens of astronomy and astrophysics, we both feel like the Arecibo site is essential. It's very well protected for radio noise, and citing an NGVLA element there is highly attractive. And so I'll stop there.
No, thank you. No, I appreciate that. And just in the few seconds I have remaining, Dr. Kennicutt, can you just elaborate on the outreach piece that I think is so important? I just can't overemphasize how I really, in many ways think I saw not just of diversity, but just the future of our country in many ways with the students that I met there. So just how important is Arecibo for that nexus between education, community, and developing STEM?
Well, I envy you. I've heard about this center for years. I've never been there myself, so I really. But your experience...
We'll make sure you get an invitation. I'll speak to. You'll be hearing from their congresswoman, I think, very soon.
First of all, there's a whole section of our report, of course, that recommends that our profession do a better job with engaging with the communities that host our key observational sites. This is an ideal example where the community is embraced. They have the outreach center that attracts, I don't have the numbers for you, of course, the number of visitors, but it's a combination of just the number of people, but it's the impact on young people, and particularly just targeting a demographic, a part of the community where we are still underrepresented. And this is just a perfect example of what needs to be done to diversify our profession. And it would be a pity to see it go. And it is such high impact for such low cost.
Well, thank you. I'm over my time. I appreciate the indulgence, Mr. Chairman. I yield.
Absolutely, Congressman. Thank you so much. If Congresswoman Stansbury is with us, I know she's still logged in. And if not, Congressman Elsie, if Jake is with us, I know we have his office, if not him. We had Mr. Brooks there for a minute. Okay, with the consent of Chairwoman Stevens and Dr. Foster, we'll move to a second round. And if our folks show up again, we will thus introduce them. So let me begin. Dr. Harrison, you guys talked about cosmological inflation, which I think is like one of the coolest things since sliced bread. I'd love for you to just talk a little bit more about, number one, how do you even begin to measure it or think about it? And number two, if our universe ends at, say, as far as light has gone, in the last 14 billion years, isn't it wholly possible that cosmological inflation has taken place in other places and is still taking place now?
Sure. Well, let me address the first the first question, which is how do you even begin to think you can detect this bizarre moment, the earliest moments in the expansion of the universe, where the expansion was so rapid, it's faster than the speed of light, if you think about it in certain ways. But it's amazing. It's thought that, and this period is absolutely necessary, by the way, to explain the absolute smoothness of the universe when we look back at the cosmic microwave background. So we have good reason to believe it existed. And we think when it happened, it created gravitational radiation, which would interact with the surface in the universe that we see when we look at the cosmic microwave background. And that would produce a particular pattern of that cosmic microwave background light in what's called its polarization, that if you can see that, it has a very distinctive signature. That will be the smoking gun that inflation occurs, and actually analyzing the pattern and its level will tell you a lot about inflation. And so it's absolutely amazing, astounding to me that there's the opportunity to probe back beyond the last surface we can actually see. And on your question of, I think you're getting at is, are there multiverses? Could this have occurred? That's not my area of expertise. I know that, yes, people theorize this, but maybe Rob has an opinion.
Just the level one multiverse.
It's not my area of expertise either. It's very highly speculative. On the other hand, inflation is an absolutely fundamental tenet of our current cosmology. If these B modes are detected, to confirm it, you've confirmed one of the cornerstones of the cosmology, which includes the cornerstone of physics as we know it. If those modes aren't detected, if they aren't there, then it means there's something really fundamentally off in physics. So hence, why this has Nobel implications.
Right. Back to the drawing board, in other words.
Yeah.
So Rob, one of the things in your guys, you talked about the neutrino observations are important understanding, and the ice cube generation 2 is making important advances, but it's beyond the charge of the Decadal Survey to recommend it. Well, were you essentially de-emphasizing the ice cube survey, or?
No, it's simply the logistics of the survey. There were 2 projects presented to us, Ice Cube Generation 2, also further technology development for future gravitational wave observatories. Those programs are funded out of the NSF physics division. We were asked by the NSF to assess the importance of those projects for astronomy and astrophysics, which we did, but they will compete for funding with all the rest of, condensed matter physics, nuclear physics, and everything else. And so we can't put ourselves in a position to tell the physicists, just do the astronomy things. That's the only reason for why we can't. It's not a backhanded compliment whatsoever. It's a statement of our charge.
Thanks. One of the things that comes up again is data across the federal government. I introduced the National Secure Data Act a month or so ago, I think with Dr. Foster, to try to get all these different databases. And we were thinking, NOAA and Census and IRS, et cetera. But what about NASA and NSF and the work you're doing? How interoperable are those databases, and what can we do to contribute to that?
Fiona, would you like to take that one?
Well, why don't you address it for the NSF side, and then I can say something about NASA.
Yeah. They're actually, astronomy, I think, is a leader in creating public data sets, and this contributes to the internationalization of astronomy. It's integrating, globalizing the whole enterprise. NSF does a very good job for the data from its national facilities, by and large. But for the telescopes that are operated by universities and institutions, more work needs to be done to make those data accessible and available in a form that is digestible readily by the community. Fiona will address NASA in a moment. There is a big challenge now with the multi-messenger astronomy and being able to access across the two, but I'll let her take it from here.
Well, Dr. Harrison, I'm happy to stop if you're.
Yeah, let's we'll come back. I'd love to hear what you have to say about it, but I feel an obligation to move on to Congressman Elsie, who's with us again. Jake, the floor is yours for questions, if you would like it.
Thank you, Mr. Chairman. No, I'm good this time. I appreciate it.
Then let's move on to our ranking member, Dr. Babin, for second round.
Thank you, Mr. Chairman. I appreciate it. Good to have a second round. I would like to address a question to Dr. Harrison. Section 508 of the NASA Transition Authorization Act of 2017 directed NASA to work with the national academies to develop an exoplanet science strategy. What impact did this have on the recently released Decadal Survey?
Yeah, so it was highly impactful. What this report did was it did an in-depth study across opportunities and exoplanets and also considering astrobiology. And it had findings about what would be the forefront areas. And so this was really our starting point along with our own panels. And so we took that report very seriously. And in fact, you'll see some of our top recommendations mirror what they said, which is top priority really is to look for signatures of of life on other planets. Here's the roadmap that we think is required. And we adopted many, not all, but many of their recommendations. So yes, it was highly influential for us. And I think a good model going forward for the agencies to ask in complicated areas, to ask that national academies to do preparatory studies, which just help the surveys.
Okay, thank you so much. And let's see, the next question I would have would be to address to Mr. Russell. The Great Observatory's Mission and Technology Maturation Program proposed by the 2020 Decadal Survey is intended to invest early in technology maturation efforts to reduce risk and decrease the likelihood of cost and schedule issues with the telescope development. How should these activities be accounted for? Should they be included in the program baseline commitment for cost and schedule estimating and tracking? Or is this a way to remove program content from the underlying project to make it appear to cost less than it really does? I would like to see what you think about that.
Yeah, thank you for that question.
Yes, sir.
Certainly, I think there's a lot of promise in that maturation effort, and to the extent that it can deliver technologies that are at a sufficient maturity level. Usually we look for TRL 6 by preliminary design review. That's going to help strengthen the NASA projects going forward. But in terms of accounting for some of those costs, we've seen some good practices, I think, with the Roman Space Telescope, the Corona instrument. There was a recognition that it might be easier to manage it as a technology demonstration, and that's what NASA has done, and they're effectively tracking those costs. But then we've seen other examples with the Space Launch System where it might be good for the next block 1B. We recommended that they set a separate baseline because it's such a significant effort that they separately track and provide oversight of some of those key efforts.
Okay, thank you very much. And Mr. Chairman, I think that concludes my questioning. So I'll yield back.
Thank you. Thank you, Ranking Member Babin, very much.
Thank you.
Let me recognize now Congressman Foster from Illinois. Dr. Foster.
Thank you, Mr. Chairman. I guess I'd like to follow up for a moment on the chairman's question involving gravitons. It's my impression that LIGO and similar projects are looking not really for the quantum nature of gravity, but since looking essentially at the classical limit that, these are quantum states with enormous quantum numbers and just coherent states with huge. And are there, first off, is that a correct impression? And are there efforts anywhere that have a realistic chance of getting at the quantum nature of gravity at this point, or is that still looking out of reach?
Yeah, I'm happy to take a crack at that. Yeah, absolutely. You're completely correct. I think what I was saying about LIGO is the one, measurement it can make is the speed of travel of the graviton. Sure. And is that close to the speed of light? And that's obviously an important measurement, but it's not getting at the fundamental nature of quantum gravity. And yes, actually, rather amazingly, there are efforts related, in fact, to things that come out of quantum sciences efforts, quantum information, quantum matter, intersecting with high energy physics that are developing new theories that can actually be tested, searching for the quantum nature of gravity. And I'm not an expert, but I know that, for example, there's an effort in DOE to build a very sensitive interferometer that can actually look for some effects of quantum gravity theories at the very low energy scale. So it's a very active field. It's been a big mystery in physics, as you well know, for
for forever.
Forever.
So we still need a great new idea to get at the graviton.
We do.
Right, back to the prosaic here. Dr. Kennicutt referred to what appears to be a sort of trend for larger cost growth in NASA-based experiments than in NSF-based or NSF-DOE-based. And I wonder, is that just attributable just to the difficulty of operating in space? Or are there structural, maybe this is a question for Mr. Russell, that are most of the, really large cost growth that we've seen in experiments due just to things that wouldn't happen if it wasn't in space?
Certainly, the environment of space is very difficult, and a lot of what NASA is doing with their science mission is one of a kind. James Webb Space Telescope is a good example, pushing the edge of the possibilities. So I think where we focused is you're always going to have that risk, and your acquisition process is really intended to manage that risk, not eliminate it. So just things like having sufficiently matured technology to really determine your requirements, make sure you have resources that match those requirements before you start, bending metal and building things.
So it's more complicated than just space versus non-space.
Exactly.
That there are maybe management differences. And when you're looking at sort of decadal survey level of thing, very often there is competition between space-based and ground-based ways to do the same physics or astronomy. And so when that happens, you're talking about, if you're going to say, okay, we're going to take this project out of space-based and move it to ground-based or vice versa, you're actually going up through this committee in terms of, moving authorizations from one potential pot of money in one agency to another. How do you deal with that? Do you operate separately? We have this pot of money that we're going to spend on the ground and this pot of money that we're going to spend in space, and just use those as input to your deliberations? Or do you actually make recommendations that involve, moving, ground-based versus space-based monies around?
Generally, when we are given, of course, separate budget profiles for the agencies which we have to meet. So in the last steps, those budget analyses are segregated. It's not often that we have competing missions on ground and space aiming at the same thing. In this case, in the case of cosmic ray background, we did have proposals on both sides. And we just—
I think there were competing dark energy proposals, if I recall correctly, for ground-based versus space-based operations.
So we asked the first test is always asking, you use the input from the science panels. The steering committee does a scientific assessment of the two options. Very often, there's always differences in what you're going to get from the two and often it's a matter of deciding the phasing. But Fiona, perhaps you would want to?
Well, yeah, just very quickly, we take the complementarity of ground and space observations into account when we make recommendations. And if we look at the, quest to find life outside of our solar system, there the very large telescopes on the ground and the space-based thing are absolutely complementary, because on the ground you can do the small stars. In space, you can do the sun-like stars. And you can't do the smaller stars from space. You can't do the sun-like stars from the ground. You need to have the whole gamut to answer this question. And so we consider complementarity like that. We try not to replicate capabilities. So for example, in our time domain program, we say NASA, do in space those time domain things that you have to do in space: X-rays, gamma rays. They can't get through the atmosphere. On the ground, do the optical, do the infrared.
Yeah, thank you. Because our committee needs a more systematic way in the cases where you have to move the balance of effort between space-based and non-space-based. And we actually, I don't see a clear picture of what that mechanism might be. Thank you. My time's up and yield back.
And Congressman Foster, if you want to stay for another round, we have them captured for the moment. And we're in the Zoom where it happens right now. But let me recognize Congresswoman Stansbury from New Mexico. Melon, if you have questions for our distinguished panel.
Yes, good morning. And thank you, Mr. Chairman, for convening this very important and interesting discussion this morning. In my community and across New Mexico, we are so privileged to have the ability to step into our backyards and look up at the night sky and see exactly what has inspired countless generations to study the cosmos and get where we are today, able to peer into the far reaches of the universe and study objects that are light years away, and able to see and understand extraordinary events that help us understand the universe and our place in it. New Mexico has been home to advanced astronomers dating back millennia, from the ancestors of our indigenous communities who were guided by the stars in creating great cities and trade networks, to the generations of physicists and astronomers who have worked to understand our place in the universe, including those who have worked on the Very Large Array in central New Mexico, the Sunspot Observatory in southern New Mexico, and laboratories and universities across the state. So as we look forward to the next generation and the next decade of studying space and what it can teach us about our place here on Earth, the next generation Very Large Array in particular will help to fuel discovery, to help to create jobs, and to inspire countless New Mexicans to pursue a career in science. So I'm particularly interested in the next generation VLA and the plans to upgrade and merge this facility with antennas across the country in order to increase our capacities in radio astronomy for decades to come. Like the current Very Large Array, the next generation VLA will contribute to new discoveries well into this century. And if we follow the guidance that's laid out in the Decadal Survey, we'll also be able to ensure that space research and discovery truly reflects and benefits all of our communities across race, gender, and community lines. While the next generation Very Large Array will directly create 200 manufacturing jobs, many of which will go to New Mexicans, the project also provides aspiring scientists with the opportunity to train and conduct research with some of the most sophisticated equipment in the country and in the world. And students visiting the VLA, such as myself as a youngster, will also be inspired to pursue careers in STEM and help to fuel the next generation of discovery. So I look forward to supporting this committee's work to advancing priorities from the Decadal Survey and to empower the scientific community to continue to expand our understanding of the universe. And as New Mexico's space research and commercial industry continues to grow, I'm excited about the groundbreaking work that will come out of our communities and how it can contribute to our understanding of the cosmos. So with that in mind, I just want to ask a quick question to Dr. Kennicutt. I'm very interested in, as I noted, in the survey's recommendations for the next generation VLA, and I'm wondering if you can talk to us a little bit about the significance of the expansions of this network and also some of the scientific discoveries that may be advanced by this facility.
Yeah, this telescope will be transformational for radio astronomy. It will have anywhere from 10 to 100 times the scientific power sensitivity of the current VLA, depending on, of course, how you measure things. The kinds of science that will enable is, we've talked about imaging planets around other stars in visible light and in the infrared. In the radio wavelengths, you can image planetary system, planets in the process of formation. And actually, in the proposal, it's envisaged by taking radio images over time, you will actually be able to watch the development, motions, planet formation literally in action, just as one example. In the case of the ecosystem science, we talked about part of the feedback that shapes galaxies is radio jets emitted from these supermassive black holes, and NGVLA will map those with unprecedented sensitivity and resolution. I'll stop there because I know your time's limited, but happy to follow up.
Yeah, I can very briefly add that I'm really excited about it for the new windows, because one of the most astounding things about this gravitational wave merger of neutron stars was that there was radio waves the VLA was able to monitor over time, which showed us that there are jets of particles going nearly the speed of light emitted in this merger. And that's to see these at the distances of the upgraded gravitational wave observatories is going to take the NGVLA.
Wow, it's amazing. And I'm so excited about the work that will be spawned by this survey and all of the incredible work that all of you do. And for any of you that'd like to come down and see the VLA, it's really quite an amazing thing to behold. It stretches across the mesas of New Mexico and is helping, as was noted, to fuel our scientific discovery of the outer universe. So come and visit us. Thank you, everyone.
Thank you, Congressman Stans, very, very much. Again, let me offer Congressman Elzy. Jake, if you want to jump in at all, you're welcome.
Thank you, Mr. Chairman. I didn't have a question for any of these folks. I just wanted to say thank you for spending some of your day with us. I grew up in the 80s. I grew up reading science fiction, 2001, 2010, Contact. I'm fascinated by this. It's an honor to be on a panel with Dr. Foster, who won the Rossi Prize for the things that we're talking about today. And if I asked any questions, it would just merely show that I'm a political science major and not a scientist. But I think that what the work that you do is extremely important. It's work only the federal government can do on a national level. And furthermore, it's work only that the United States government can afford to do. So it's extremely important. The work you do is important in ways that most of us can't even imagine right now. So while I don't have any questions, I've appreciated everything that you've said, and it's a fascinating topic. It's disappointing that we're a little bit behind timeline, a lot behind timeline on some of these projects, but great science is going to come from it. I look forward to meeting you all in person at some point. And thank you for the opportunity to speak, Mr. Chairman. Mr. Foster, it's a pleasure to be on this with you. And thank you all very much for your time. I yield back.
Thank you, Congressman, very much. But it is the political scientists that authorize and fund all this. We need those too.
Oh, I might add that my uncle, Lawrence Elzy, is a professor of physics at UTEP. And Dr. Foster, I don't know if you ever, or Congressman Foster, I don't know if you've ever met him, but I'm very proud to be on this. And I spoke with him that I would be on this panel today, and he said, "You're not qualified to be on this panel," but here I am. So anyway, thanks again.
Well, my daughter, in fact, lives in El Paso, and so I will make it a point of visiting the next time we're there.
That's right. And you're more than qualified to serve on this panel. I have three short questions before passing off to Dr. Foster again. Number one, in your written testimony, you talked about how the cadence of one probe mission per decade is realistic. You're looking at costs. It seems to me there have been a lot more than that just in the last decade. For example, we have Da Vinci and Veritas about to go probe Venus. And so why just one per decade?
So we were referring strictly to astrophysics probes. And this is a program that we imagine would mirror what's done in planetary science with the Discovery missions, which are probe class in the same way we imagine. And so we'd like to expand this incredibly successful model to astronomy and astrophysics. And, the one per decade really, if you look at NASA's great observatories that were alluded to in the opening remarks, these really had a whole range of scales from what we would call probe class up to flagship class. And so, achieving this broad range of capabilities really is going to be enabled by adding this line. And so again, we were just referring strictly to astronomy and astrophysics, which has never had a competed class of missions at that scale before.
And one more thought, with the Mauna Kea telescope was all interrupted by the protests over how indigenous people were built into it. And you all were developed a community astronomy model of engagement. Is there anything that we can do here in Congress on a bipartisan effort to help with those community astronomy models? I mean, should there be?
Bob, do you want to take that one?
Yeah, it's an excellent question that I don't have an immediate answer for. That recommendation was largely aimed at our professional community. Subjects like archaeology obviously have activities on cultural sites, sensitive cultural sites that are very sensitive, and those professions have developed sort of codes of interaction that help. We don't think every new project should be in reinventing the wheel, and that's the nature of our recommendation. I think something endorsement or from Congress could be very helpful, but I'd have to think about it a little longer, to be quite honest with you, sir. It's a really, really good question.
Yeah, I mean, and if there are things, we'd be happy to follow up with you after the hearing if things come up.
All right. Yeah, thank you. I'm sorry, I'm running the office by myself too while we're doing this. Did you get it? Okay, thank you.
Yeah, well, to Phil, of course, the NSF does become a partner in the 30-meter telescope project, and Mauna Kea is still a site under consideration. Of course, the federal government will have a role, of course. It will have to meet certain, guidelines, the broadly interpreting environmental impact and cultural impact and so on. So I think that is an area where, government involvement will be critical. But that's a rather lame answer, I suspect.
No, it's fine. It was a lame question. My last trivial question, Dr. Harrison, when you're talking about inflation theory and how you had this uniform background radiation, so it actually isn't perfectly background uniform, or else we wouldn't have had the galaxies form. So one of the interesting speculations is, was it the original quantum variations at the very beginning that created enough variation to give us the rest?
That is indeed at the heart of it. And when I said smooth, yeah, it's obviously not perfectly smooth, but if you look at the cosmic microwave background, the fluctuations are really tiny. And it means somehow that whole surface was in causal contact at some point. And that's sort of what leads to the idea of inflation. But you're right. I mean, it's absolutely astounding that those tiny, tiny little fluctuations somehow grew to the amazing density variations we see today in the universe. And that is, I don't know, Rob, you can chime in, but to me, it's amazing. Tremendous progress has been made with numerical simulations and understanding dark matter's essential role. But yeah, the seeds of these tiny fluctuations probably came from inflation.
Yeah, 1 part in less than 1 part in 100,000. And if not for the quantum nature of matter, we wouldn't be here. It's quantum fluctuations that grew. Those were the seeds. It's amazing. I agree.
Well, I would argue that Bill Foster is way rarer than 1 part in 100,000. So let me give you the final word, Dr. Foster.
Well, thank you, Mr. Chair. I'd like to speak a little about the issues about optical and radio interference and the degree in which these may become mission threatening, to the extent that you may have to start incorporating them into your decadal planning. One of the projects that you recommend is prioritizing the Cosmic Microwave Background Stage 4 Observatory, or CMBS4, which is the next generation ground-based cosmic microwave background measurement. This project is of some parochial interest, since although it is a collaboration among a large number of institutions, there are several in Illinois, like Argonne National Lab, Fermilab, University of Chicago, and University of Illinois at Urbana-Champaign. Now, earlier this year, the full Science Committee had a hearing on spectrum needs for observations in Earth and space science. And the hearing mostly focused on weather science, but it really highlighted how anytime you're doing noise-limited measurements, you have to worry a lot about man-made interference. This has also become an issue with these satellite constellations that are now being talked about and in fact being launched. And so, at what point does that become something that you have to, you're going to need a model for how the world public will behave, and whether we're really going to be willing to, sacrifice the performance of our cell phone system for scientific purposes. How do you, well, first of all, how close to being a critical issue is that, where you can say this is a great experiment, but it's just not going to be possible 10 years from now? Are we anywhere near that point?
Should I start and then you take it on? I think, in the radio, this problem has been around for decades, and the NSF in particular, coordinating with other international bodies, has done an excellent job of regulating. It's one reason we have these radio quiet sites in Arecibo and Green Bank and Socorro and
I have to say, it just sounds like heaven to be in one of these places where no one is allowed to have a cell phone.
That's right. But now the problem is, 5G, of course, is eroding more and more of the spectrum itself. But the satellites are everywhere. If the satellites start broadcasting in these frequencies, that is the real game changer. And maybe Fiona, you can address the optical satellite constellations in a moment. But it's way above our pay grade to know how you regulate. As you say, this impacts human act if you were absolutely strict. And it's also international. It does no good at all for one country, us to set rules if every other country in the world, of course, has satellites flying over us that follow a different set. So I think this is one reason we think government action, whether it's through the executive agencies or through Congress, is absolutely essential. And we think our best role is to empower the NSF, NASA, to the extent it may need to be involved, to providing you with the information that's needed. And
so at least we can quantify, here is the damage to science as a function of what is deployed. And I think you rightly point out it's an international issue. I'm very encouraged the Biden administration is really focused on engaging internationally on a number of fronts, and that's clearly should be.
To answer your question, it's not catastrophic yet, but if current trends continue, it could be.
Okay. What about optical?
Yeah, so the most recent issue is things like the Starlink network from SpaceX, which aims to provide cell phone coverage all over the globe through very, very large arrays of satellites. And the issue here is that, especially at dawn and dusk, you get glint off of them and you see them as streaks of light. In fact, you can go out, if you're in a dark spot. I live in LA, so I'm not, but you can see these streaks very prominently. And the Vera Rubin telescope is struggling with this a lot because their wide field surveys will be contaminated with these streaks, and they have to figure out how to deal with it. There are mitigating things to do. In fact, there was a hearing in which Elon Musk sort of listened in, and they did try to paint them black, but this is a global problem. And going back to representative from New Mexico's point, this could change the way we as humans experience the night sky, right? What does it mean if you go to the desert and you look at the horizon and you see these streaks of light, and that dominates over the stars and the sunset? And so this is a problem, I think, that, again, Congress and legislation is going to have to try, and international cooperation is going to have to try to deal with. And I think it's not catastrophic yet. The Vera Rubin telescope has found ways to deal with it, at least at the levels they are now. And I realize the time is up, but I just want to very quickly point out planetary protection has had similar challenges. This is, spacefaring nations that send probes to the planets don't want to contaminate them with, microbes or things that might be interpreted by a future generation as life. And that's coordinated through the COSPAR. And so there are models where, there is cooperation to try to protect our precious scientific resources.
Yeah. So I think just collaborating with your international colleagues to at least quantify the damage so that policymakers understand the trade-off they're making and not just sort of stumble blindly into it. Anyway, my time has expired. I yield back and thank the chairman for a very good hearing and our witnesses as well.
Yeah, thank you, Dr. Foster, very much. And we are coming to the end. I just, before we bring the hearing to a close, I just want to thank you for testifying. This is my favorite hearing of my 7 years. And thank you so much for reading the 835 papers that went into putting the Decadal Survey together. Thank you for co-chairing it. Mr. Russell, thank you for keeping us all on track and spending within our limits or something like that. And the record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may want to ask the witnesses. So with that, the witnesses are excused. The hearing is now adjourned. We're formally over.